For this video, we're going to try to construct p orbitals from the spherical harmonics, using primarily the spherical harmonics, the YLM, also called the Legendre polynomials. So you may recall from prior chemistry courses that the two p orbitals have a principal quantum number of 2 and an orbital quantum number of 1. If you haven't run across that before, or at least haven't seen the L quantum number before, that's fine. So we're introducing it here. L equals 0 corresponds to the 2s. So L equals 1 corresponds to 2p. L equals 2 shows up in the 3 d orbitals. So in trying to construct our 2p orbitals, first of all we have the radial part of the 2p orbital, the r-dependent part. And that's given by the R21 wave function that we discussed in the previous video. And what we haven't covered yet is the angular parts of the p orbitals, the y10, y11, and y1 minus 1. And those are the three possible YLMs, because the rule is if L is equal to 1, then ML can take one of 3 values. It can go from -1 or 0 or 1. It can have one of those 3 values. And thus we have these 3 angular momentum wave functions, angular momentum eigenfunctions, y10, y11, and y1 minus 1, the spherical harmonics. And these are, you may recall, eigenfunctions of the L squared operator, the angular momentum squared operator, and the LZ operator, the component of the angular momentum along the z-axis. Okay, so first let's look at y10. The y10 is proportional to cosine theta. And if you recall, theta is the angle with respect to the z-axis. So if we have a vector r, then theta is the angle difference between the vector and the z-axis. And so if y10 is proportional to cosine theta, that means it's going to have a maximum at theta equals 0. So that would be along the plus z-axis. And then it's going to go to 0 at theta equals pi over 2. And then as you go down to the 180 degrees or pi, it's going to have a value of -1. And so as a function of angle, this wave function, first of all, it's real valued. It does not have any complex components, the y10. It's some normalization constants and cosine theta, and it has no phi dependence. And so it looks like this is an orbital that is sort of oriented along the z-axis. The wave function would have a positive value along the plus z-axis and would have a negative value along the minus z-axis, and it would have a nodal plane in the xy plane. So that means the wave function would be 0 everywhere in the xy plane, and it would be positive above the xy plane along the plus z-axis, and it would be negatively valued along the minus z-axis. And so this corresponds to what we typically think of as a pz orbital. Okay, so we can look at this in part as to we can look at these three YLMs and try to figure out which one's the X and which one's the Y and which one's the Z. It turns out it's not quite that simple. We picked the simplest one first. So one of the YLMs gives us an angle dependence that when we combine that with the radial dependence, which is this kind of exponentially decaying function, we end up with this kind of roughly spherical cloud of probability, but with a nodal plane cutting through the middle of it where the probability goes to 0. And so there's sort of two sort of two kind of half spheres that have some probability density, but half fuzzy spheres. And this is often sketched using these kinds of kind of balloon animal drawings, where you, of course, they're not balloon animals. They're a simplification of a contour plot of a complex or a complicated three-dimensional function, where we set some sort of contour value and then shade inside that contour value, and or take a projection of that contour value onto the drawing surface here. And another convention is that where the wave function is negative, we often hatch in or shade the negative part. Okay, so when we multiply this YLM times the R21, and then take a contour plot and then keep one of the contours, depending on which one you get something that looks a little bit like one of these kind of balloon animal drawings. But of course, this is just a simplification of a rather complicated three-dimensional function that it has an exponential component in the radial part and has this factor of cosine theta. Now, for the 2px and 2py, it turns out that the y11 and the y1 minus 1, the two spherical harmonics that we have left, don't neatly give you the 2px and 2py orbitals, and we actually have to sort of construct them from linear combinations of the y1 minus 1 and the y1 1. Because the y1 these functions by themselves are not real valued, and so they're difficult to plot. But by making sums or differences of these wave functions, and maybe multiplying by I, we can end up with a real valued function that we can sort of plot. And it turns out, so we can think of this as a mathematical approach to giving us a drawable, a wave function that we can draw, but there's perhaps some deeper stuff going on here. So let's first of all look at our y1 plus or minus 1. They're functions that are proportional to sine theta e to the I m phi. And again, in this case, m isn't just something that is just m or that could have any value. It has two specific values. It's either plus 1 or minus 1 because it's that value after the comma in the YLM. In other words, so this is just a perhaps confusing way to write these two equations. Y11 is proportional to sine theta e to the I phi, and y1 minus 1 is proportional to sine theta e to the minus I phi. And you may recall Euler's formula. And if you don't recall it, it's not much of a problem. It's fairly straightforward. Complex exponentials are like e to the I phi is cosine phi plus I sine phi. And e to the minus I phi would be cosine phi minus I sine phi. So based on Euler's formula, we can construct a real valued 2px wave function. So our first of all, our psi 2pz is y10, r21. Then our psi 2px is going to be 1 over square root of 2 y11 plus y1 minus 1 Okay, and then when you plug in, use Euler's formula on this, uh, the sine phi parts cancel, and so you end up with something that is proportional to, again, this is the proportionality sign here. It's proportional to sine theta cosine phi. And phi is the angle with respect to the x-axis of the projection of a vector onto the xy plane. And so this corresponds to a wave function that is oriented along the x-axis. It's got its maximum value on that axis, and it decays as you get further away from that axis. And there's going to be a sign change when you go from, there's going to be a nodal plane in the YZ plane because of the way cosine phi works in our spherical polar coordinates. Okay, so then our psi 2py, in order to get something similar to this, but not complex, we need to multiply by minus I over square root of 2, I11 minus I1 minus 1. And then again, we would also have the radial component, R21. And this, because we have a difference in sign here, this would, the cosine terms in the Euler's formula would cancel, and we are left with the sine terms, which would not cancel. And so we get something that's proportional to sine theta, sine phi. And so this is corresponds to the y-axis. Another way to look at this is you remember our transformations between spherical polar coordinates and Cartesian coordinates. That x is equal to r sine theta cosine phi. And of course, this looks a lot like this proportionality sine theta cosine phi that we see for psi 2px. So just by kind of pattern matching without going back to the full diagram and thinking about where the nodal planes, if that's confusing to you, you can do this kind of inspect and compare to the relationship between Cartesian and spherical polar coordinates to tell you which axes things line up on. And again, y is r sine theta sine phi, and z is r cosine theta. And so again, by just comparing these relationships to the functional form of these various wave functions, we can see which one belongs with which axis label. And the radial part, I already discussed that. So these p orbitals are these kind of fuzzy blobs with a nodal plane somewhere. You can kind of represent them using these kind of dumbbell shapes or peanut shapes, or kind of cartoon animal shapes. But you can also think of them as kind of a fuzzy blob of probability that's roughly spherical, except that it has a nodal plane in the middle of it that kind of divides it into two lobes, two sort of hemispheres, like kind of like halves of a brain or something. And again, I don't mean to trivialize this notion of the pictures that you've seen that that look sort of like balloons or something. Those represent the more complex structure, and they give us a simpler way of representing the shapes of these orbitals pictorially, which can definitely be helpful later, when you're trying to, say, construct molecular orbitals out of these atomic orbitals, that sort of thing. Those pictures of 2p orbitals are not, they're simplifications. They're not really wrong. Okay, and let's see, what else can we look at? So, and I'll leave it as an exercise for you to, again, go through and see when you apply Euler's formula to see that these give you this kind of angle dependence. So, then the question is, why do we even bother ourselves with the YLMs, with these spherical harmonics? And the reason is these are so why not just have 2px, 2py orbitals? Why do we have the YLMs? And the answer is the YLMs are eigenfunctions of the L squared operator, angular momentum squared, or sort of the total angular momentum operator, and the Z component. Oh. Of the operator. Now, are the YLMs eigenfunctions of L squared and LZ? Let's take a look. So it kind of seems like, maybe they could be. It kind of depends on how the math works out. Certainly, it seems possible that if you construct a new function out of other functions that are eigenfunctions of an operator, then maybe the new function would be an eigenfunction of both of those operators. But maybe not. We kind of have to run through and see. So first of all, let's look at the L squared operator, the sort of total angular momentum operator. Gives you the sort of what's the overall angular momentum, what's the magnitude of that vector, the angular momentum vector, irrespective of where it's pointing. And so if we act L squared on a 2px, and we're going to strip out the we can strip out the radial dependence because L squared doesn't really act on the radial part. So we're going to represent this as just the 1 over square root of 2 And when we distribute this over both components of this wave function, we're going to have L squared y1, 1 plus L squared y1 minus 1. And you may recall that L squared, when it acts on, so this is something, both of these we can evaluate. And you remember L squared acting on y, Lm equals L times L plus 1, h bar squared, YLM. And so what we have to do then, when we distribute the L squared over both of these instances of the YLMs, the Y11 and the Y1 minus 1, we have to look at the number before the comma, and that tells us what value to use for L in each instance. So that's going to give us 1 over square root of 2, and acting L squared on the y11 gives us 1 times 1 plus 1 h bar squared, or 2h bar squared, y11. And again, L squared acting on the second one gives us the same value. Right, the m quantum number, the minus 1 there, doesn't affect the L squared value, because the m quantum number is telling you something about the direction of rotation, and the total angular momentum operator doesn't care about the directionality of the rotation, just the sort of how much rotation is going on overall. Okay, so we get 2h bar squared. Right, we can factor that out. 1 over square root of 2 y11 plus y1 minus 1. And of course this is at least the angular part of our psi 2p 2px. And so we have that it is an eigen it is an eigenfunction of the L squared operator. Great, so far so good, right? And of course, since the L squared operator only depends on that first integer in the YLM, the L quantum number, and the L quantum number is always 1 for the 2p orbitals that we've constructed. It's the M quantum number that varies. So therefore, it looks like it's going to be the 2px, 2py, and 2pz are all going to be eigenfunctions of the L squared operator. But in the case of the LZ operator, it's more complicated. So let's act LZ on 1 over square root of 2 y11 plus y1 comma minus 1 comma minus 1, and that's going to give us, and if you may recall, LZ acting on y11 gives you plus h bar as the eigenvalue, whereas LZ acting on y1 comma minus 1 gives you minus h bar as the eigenvalue. And if you need a reminder where that comes from, the LZ operator is minus I h bar d phi, and we know that our YLM is going to be some function of theta times e to the im phi. Okay, so without putting those two facts together, you can get that LZ acting on Y11 is going to give you plus H bar, and LZ acting on Y1 minus 1 is going to give you an eigenvalue of minus H bar. Okay, so then when we distribute, so then back up here, so then when we distribute our LZ on these two operators, we're going to get 1 over square root of 2 LZ Y1 1 plus LZ Y1 minus 1. And here's where we have to be very careful to instantiate. If we just use the notion, oh, LZ acting on YLM gives you MH bar, and we don't instantiate, we don't actually put the actual value of M in that instance, then we're going to get a wrong answer. So in this case, that's going to give us, the first one's going to give us plus H bar, Y11, and the second one's going to give us minus H bar, Y11. And this is not, so we've introduced a minus sign, and there's no way to, you can't, if you multiply the whole function by minus 1, that's not going to, you're not going to get back basically acting LZ on this 2px wave function gives you a different function. In fact, what it ends up giving you is a 2py wave function, which is interesting. So LZ acting on a 2px wave function has the effect of rotating the wave function by 90 degrees. Okay, but then that's a new wave function. It's not the same wave function we started with. So it's not an eigenfunction. It's actually changed the function. We get a new function, one that's rotated with respect to the original function. Now the fact that it's rotated is kind of interesting in that it gives a little bit of a hint as to something important about the angular momentum operators, which is that angular momentum operators actually generate rotations. And this is one of the ideas that that comes up in sort of the quantum mechanical version of M.E. Noether's theorem about regarding that conservation laws, specifically in this case, conservation of angular momentum, arises from a continuous symmetry. And the way that's proven is by one of the pieces of Noether's theorem, which established that the various operators for, say, angular momentum is actually causes rotations. Anyway, so that was just a little side point. But let's get back to where we were. So so it's so therefore these 2px and 2py wave functions are not eigenfunctions of the LZ operator. So that's why we have a couple of different kinds of representations. Sometimes we want to have we want to represent our system. It's convenient. It makes it for easier calculations if we build up our wave functions using eigenfunctions of, say, the LZ operator. In other words, if we use the YLMs. Other times, it may be more convenient to sort of line up our orbitals along the various axes, along the various Cartesian axes, x, y, and z axes, in which case we should use the 2px, 2py, and 2pz wave functions, and we can kind of go back and forth between them. They're related by these linear combinations. So why do we care about eigenfunctions of the LZ operator? And the answer is the 2p orbitals are degenerate. They all have the same energy for an H atom by itself in a vacuum with no external fields. However, if we turn on a magnetic field, it splits the degeneracy, and some of the states go up in energy and some of the states go down in energy. And you can actually see this if you take a discharge tube for hydrogen, say, and place that tube in a strong magnetic field, you'll see new lines appear, and this so-called fine structure, and due to something called Zeeman splitting. And so it turns out, though, if we apply our magnetic field along the z-axis, then the YLMs are still going to be, the 2px, 2py orbitals are not going to be eigenfunctions of the Hamiltonian in the presence of a magnetic field, but but the YLMs are. In fact, in the Hamiltonian, you know, in the presence of a magnetic field, essentially the orbital angular momentum associated with electrons rotating along in various directions is going to give rise to a change in the energy levels, but you'll still end up with a Hamiltonian that is where the YLMs are eigenfunctions of the Hamiltonian. So the Hamiltonian for this case is going to be the Hamiltonian without a magnetic field, which we'll call H0, plus E B LZ over 2 times the mass of an electron, and where E is the charge of an electron, B is the magnetic field strength, and this is assuming that we have our magnetic field oriented along the z-axis. So we're just going to, so essentially we define our z-axis as the axis that the magnetic field is oriented along. This Hamiltonian, the YLMs are still valid solutions to this Hamiltonian, as can be shown. We won't do that right now. We'll do that later because there's some other wrinkles to this problem. So we'll come back to that. Because this isn't actually, this is just a partial Zeeman Hamiltonian. There's also electron spin, which we haven't introduced yet. So we'll introduce that and discuss the full Zeeman Hamiltonian. However, I just wanted to motivate why we still keep the YLMs around the spherical harmonics is because the spherical harmonics are still eigenfunctions of the Hamiltonian even when you have a magnetic field. Okay, let's do one more thing before we go. Now, can we still measure LZ for a 2px? Does it exist for a 2px orbital? Sure, we can. We measure the z component of the angular momentum. Yeah, we can do that. So we don't have an eigenfunction of the LZ operator, but we can still calculate the expectation value. And we could also even look at the LZ squared and the variance for momentum along the z-axis. And this is a exercise that I'd like to go into, take a little detour here to discuss this, because I think this gives us a nice demonstration of an important quantum mechanical principle and some important early experiments related to quantum theory. So let's look at this. So our LZ is going to be given by the integral of our psi 2px wave function okay, and we're gonna neglect the R the R2 ones, the radial parts of the wave function, because we can integrate out the radial part separately, and it's going to integrate out to 1. So and if you don't trust me, you can work through it yourself. So we end up with just the integral over the theta and phi over their appropriate ranges. And then the 2px, that's going to be y1 1 star plus y1 minus 1 star. And then we have LZ. Okay, and then distributing LZ over the YLM to the right, that's going to give us again, just repeating this, the y1 1 star plus y1 minus 1 star, and distributing that, that's going to give us h bar y1 1 minus h bar y1 minus 1 d tau, and then multiplying this out, we get an integral of, let's see, first is going to give us h bar times y1 1 star y1 minus 1. Outer, that's going to give us y1 1 and minus h bar y1 minus 1, so we get minus h bar y1 1 star y1 minus 1, and then inner is going to give us, let's see, plus h bar times y1 minus 1 star, y1 1, and then last is going to give us minus h bar y1 minus 1 star y1 minus 1. And of course there's the d tau, the differential volume element. And I should probably put this all between parentheses, but I think we all realize that the d tau applies to everything after the integral sign. Okay, so then let's look at these values. So this goes to h bar. Now the YLMs are an orthogonal set, so this integral goes to 0. This integral also goes to 0 because again these two wave functions are orthogonal, and this, of course, these wave functions they're normalized, so that it goes to this goes to minus h bar, and so we get and there's a 1/2 that I forgot here, 1/2. But it turns out that 1/2 doesn't matter too much because we have 1/2 h bar minus h bar equals 0. So half of 0 is 0, and so this is the, so yes, we can calculate the expectation value for LZ, and it's going to be 0. We can also, so we can calculate LZ, L squared, but we can also calculate the LZ squared operator. And LZ squared as an operator is just the LZ operator twice. And in other words, LZ squared acting on YLM is going to be m squared h bar squared YLM. Right, you're going to be acting it twice. Each time you get a factor of mh bar, and so you get m squared h bar squared. Okay, so let's run through that one. We're going to get the integral 1/2 the integral of okay, so we have our LZ squared operator sandwiched in between the wave function and its complex conjugate. And let's see, then acting the LZ on each of these is going to give you, so in this case, and we acted on y11, we're going to get 1 squared times h squared, which is going to be h bar squared. So we're going to get h bar squared y11. And then again, when we act LZ on the y1 minus 1, we're going to get minus 1 squared, which of course is just 1, times h bar squared. And so this time when we do the FOIL, you can see that we don't have that difference in sign. And so we're going to get equals 1/2. Sort of skipping a couple of steps, you feel free to distribute and look at each term and figure out which ones go to 0, like we did in the previous case. We're going to get h bar squared plus h bar squared, or 2h bar squared. And then, of course, we have the 1/2 out front, and so we get h bar squared. Okay, so the average angular momentum along the z-axis, the component along the z-axis, is 0. But the RMS angular momentum, right, the squared angular momentum along the z-axis is not 0. And so this this corresponds to, this is a little bit like in the particle in the box where we had momentum going to the left and momentum going to the right. So in this case, it's sort of like we can think of this this 2px state as being a linear combination of these rotating wave functions, where in one case you're rotating clockwise, and in the other case you're rotating counterclockwise, and it's this kind of dual wave state where it's kind of flipping back and forth, or this in this spooky quantum mechanical superposition, and you don't know which state it's in at any given sort of moment in time, and although it's not that you can pick any particular moment and know what it is. That's just kind of a way of saying we've got a superposition and we just don't know which one it is. Anytime you would measure a single atom, measure the angular momentum component along the z-axis, which you can do using a magnetic field, as we'll talk about shortly, you're going to get that sometimes in some measurements it's going to be rotating clockwise, in other measurements it's going to be rotating counterclockwise. And the average angular momentum component along the z-axis would be 0. But the LZ squared is not 0. Sort of like the average velocity of the molecules of an ideal gas would be 0, but the RMS velocity is not 0 because of the way velocity has sign. You can have positive velocity or negative velocity along any of the given axes. Okay, so we have a lot of variance then to our LZ. Sigma squared LZ is going to be LZ squared minus, so the spread in our LZ is given by this, and that's going to be h bar squared because we already knew that this is, of course, 0. So this means there's a lot of uncertainty or a lot of variance in LZ, and again, it has to do with this kind of dual wave state where we have a superposition of molecules that are rotating where the electron is rotating clockwise in the xy plane and counterclockwise in the xy plane. And you can actually do an experiment, an atomic beam experiment, where you take a series of atoms in a beam, and we can prepare them all and we won't worry about how to do that, but it turns out it's not too terribly hard. We can prepare them all in the 2px state, and then we can send our beam through a sorter, and for each of these, it it can send them into a different bin. If the atom has an electron rotating in the counterclockwise direction in the XY plane, then it puts it in the plus H bin, right? And then you could maybe count it using some kind of microchannel plate or you know, some kind of Geiger counter or something like that. So you could count these atoms and count which ones are plus H bar and which ones are minus H bar. Some of the atoms are going to be sorted along the minus H bar axis. And by the way, this sorter is fairly simple. It's just an inhomogeneous magnetic field. If you have like a magnet with kind of a pointy end, like an electromagnet where that's kind of C-shaped, and so the magnet, those are the pointy ends of it. And basically, the magnet's going to look like this kind of and you have a coil of wire to power the magnet, and basically that's going to give you a very inhomogeneous magnetic field, right? It's going to decay quickly as you get further and further away from the sort of pointy parts of the magnet. Anyways, if you send a beam through something like that, it's going to split up your populations this way. And so basically then by looking at your output of your reader, assuming you can record the impact of each of these atoms, and that can certainly be done. Particularly if they're ionic atoms, we can accelerate them and put them through some sort of electron multiplier and get these individual clicks or record individual events for each of these channels, and we can do sort of these are sort of single atom experiments, right, where we're looking at one atom at a time, and you can record the LZ for each one, and you're going to get either minus H bar or H bar, and you get this kind of random sequence. Maybe you get a few H bars in a row, and then minus H bar, and of course it's hard to come up with a random sequence, but that's basically giving you and on average the average LZ value, of course, is going to be 0, but the individual measurements are either plus H bar or minus H bar. And of course, if you do the statistics on a series of measurements like this, that's a very large series of these measurements, you're going to get that the variance is going to be H bar squared. Okay, so that's the physical picture of this kind of dual wave state when you have something that's not an eigenfunction of an operator. Okay, and I think that is a good place to stop. Next, we'll talk about isospin.